Hey everyone, and welcome back to the AI Research Roundup. I'm your host, Alex, and today we're diving into some fascinating work happening in AI. We'll be looking at a paper called Syzygy of Thoughts Improving LLM Quality with the Minimal Free Resolution. So, we know chain of thought prompting helps large language models reason better by thinking step by step. But this paper points out that for really complex problems, one line of thought just isn't always enough. They introduce Syzygy of Thoughts, or SOT, a new framework that adds extra interconnected reasoning paths to the standard chain of thought process, aiming for more robust and structured problem solving. Okay, so let's look at the first figure to see how this actually performs. This radar chart basically plots the accuracy of different methods across 9 different datasets, things like mathematical reasoning, general knowledge, and logical reasoning. The outer ring shows results for the 4.0 mini model, and the inner ring is for the QN 2.5 model. You can see different colors representing standard chain of thought with self-consistency, and this new Syzygy of Thoughts method. What's pretty clear is that the SOT lines, the blue one for 4.0 mini and the orange one for QN 2.5, they generally reach further out, meaning higher accuracy across most of these tasks compared to the other methods. So we saw in the radar chart that SOT generally performs better. Now this next figure gives us a look under the hood at how the Syzygy of Thoughts framework actually operates. It breaks down the process into 6 main parts: module, Betty number, freeness, mapping, exactness, and minimality. Essentially, it starts by analyzing the problem, figures out its complexity, generates extra conditions or hypotheses, maps out different reasoning paths, checks if everything is logically sound and complete, and finally, tries to find the simplest, most efficient, correct answer. It's this structured decomposition that aims to deliver those accuracy improvements we saw. Okay, so building on that framework we just discussed, this next figure, figure 4, gives us a more concrete, conceptual example of how SOT actually guides the LLM. It shows it like a chat, where the LLM first analyzes the problem, that's the module part, then figures out how many extra conditions it needs, which relates to the Betty numbers we mentioned. You can see it generating those conditions, mapping out strategies, checking if they're logically sound and minimal, eventually arriving at the final answer. It really visualizes how those abstract steps guide the reasoning process. Okay, so we've seen the conceptual flow. Now this figure takes a closer look at one of those specific components we mentioned, the Betty number. Remember, that relates to the complexity and the number of extra conditions needed. This chart plots the accuracy against different Betty numbers along the bottom for different values of the mapping parameter, which is how many reasoning paths are constructed. You can see that accuracy generally goes up as the Betty number increases, but it seems to level off after a certain point, around 7 or so. It suggests adding some complexity helps, but there's a point of diminishing returns. So we just saw how the Betty number affects accuracy, showing there's a sweet spot for complexity. Now, this next chart looks at stability. It shows the accuracy of SIT across all those different data sets, but this time it plots accuracy against different temperature settings along the bottom. Temperature controls how creative or random the model's responses are. What's really interesting here is that the accuracy lines for SOT are relatively flat across the board, meaning the performance doesn't really drop off much even as the temperature increases. The paper points out this shows SOT is quite stable compared to standard COT, which can be more sensitive to temperature changes. So we just saw how stable SOT was across different temperatures. Now this figure, figure 8, provides the comparison point. It shows the same plot, accuracy versus temperature across those datasets, but this time specifically for the standard chain of thought method. And well, unlike the relatively flat lines we saw for SOT, you can see here that the accuracy for standard COT fluctuates much more significantly as the temperature changes. Some lines dip quite sharply, especially towards the higher temperatures. This really drives home the point that SOT's structured approach seems less sensitive to that generative randomness compared to the baseline COT. So seeing that comparison really highlights the stability advantage of Syzygy of Thoughts. Overall, This paper introduces a fascinating way to structure chain of thought reasoning using ideas from algebraic topology. The key takeaway is that this structured approach makes the reasoning process more robust and stable compared to standard methods. It's important work because it offers a mathematically grounded path towards more reliable, complex reasoning in large language models. That's all for this episode. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.